All right, still working in section 5.2, and if you have not already done so, make sure that you have viewed the review video on summation notation before you watch this video. It will kind of make our transition a little easier into what we're going to be doing. You definitely need to understand sigma notation and how that works for this section of notes. Now, coming into this, kind of talking about our steps of overview or big picture of what we've done so far, is that we started out in calculus, first recognizing that calculus itself is this idea of using a limiting process to help us calculate some things that may seem to be uncalculable before we start. That we wanted to come up with this idea of how to find an instantaneous rate of change, which we initially struggled with, that we couldn't figure out how to determine how fast one was going when you were only given 1 point on a curve. But using an idea of a limit, that we could use the average rate of change and a limit as our change in time gets smaller and smaller to help us come up with an instantaneous rate of change. And so that first half of calculus was basically using the concept of the derivative in order to create a formula for finding instantaneous rate of change. Now, when we looked at that derivative, we first developed the idea of what it was, and then we had a limit definition, the long way of calculating the derivative. And then before we moved into applications, we needed some shortcuts, so we created some shortcuts that were going to help us calculate a derivative or instantaneous rate of change without having to do the limit process. All right. Now what we're doing is we're looking at the second part of calculus. And you've seen from section 5.1 that the second half of calculus is very much related to the first half, in that we started by looking at working backwards. That if I were to give you the formula for the derivative, could you work backwards and find an antiderivative, a formula for the function that you must have had that gave you this instantaneous rate of change? So I'm giving you rate of change and you're working backwards to, say, a position function when we're looking at it. And so we started with that, and we looked at indefinite integrals. And remember that in section 5.1, there's the process of finding the antiderivative is going to be called this integration. If you have this indefinite integral, your job is to find a general antiderivative, which is where we have that plus c, that constant of integration, that there are many functions that have the same derivative, and we know that because the derivative of a constant is 0. So we find the general antiderivative with our plus c, and then if we wanted a specific one, we would have to be given some initial conditions, some information to help us set what the constant is, to help us set which of the many functions you must have been on in order to start with, and I have to give you that information. Okay, and so now this second question, kind of this idea of developing what we're actually doing here, we're actually going to start by looking at this idea of finding area of irregular regions. And what we mean by that is that instead of having a known geometric figure like a triangle, square, rectangle, circle, we might be trying to find the area, say, in between a curve here in the x-axis, between the curve and the x-axis. I'm trying to find this green area right here, which obviously is not any known figure. And so we start to think about what are some things that we can do. And we also keep in mind that we're probably going to use a limiting process somewhere in this, because we're in calculus, and calculus is about using the limiting process in order to find uncalculable items, or what we think might be uncalculable. All right, so a couple of suggestions. If I had a class here, students typically want to basically section this off and create shapes that they know, like maybe draw in some figures and some triangles and try to piece those together. Another way of, kind of from prior knowledge of what we've been doing, and we've been working with this a little bit, is this idea that we can use rectangles. That what I can do is I can maybe draw a rectangle, and I'm going to use a rectangle that uses the height of the rectangle is going to be the right endpoint on an interval. Like say for example, let's do for this n equal to 4 rectangles, just to kind of give some ideas of what we're going to do. So I'm going to draw a rectangle, and of course I'm dividing into 4 because I very nicely divided my interval of interest 0 to 2 into 4 sections. So if I kind of think about using the right portion, the right endpoint of the interval to give me the height of the rectangle, then this could be one rectangle I use to calculate area. And then I'll use the right endpoint over here and drop the altitude down and draw a second rectangle here. And continue the process over until I get 4 rectangles, which of course the advantage of the rectangle is that it is giving me something that is easy to calculate area. However, is this a great estimate of the area? If I was thinking about this and using the height equal to the right endpoint on the interval, in this example, it would be an overestimate of the area. So then sometimes we come in and we say, well, I don't always have to choose the right endpoint. Maybe I should choose the left endpoint. So option number 2, so that was option number 1. Option number 2, I'm going to get my height of the rectangle by using the left endpoint on the, I guess I should call these subintervals because I have divided it into 4 sections. So now if I use the left endpoint and we draw a rectangle, and maybe I'll just shade it so that we can kind of visualize this coming across. Now in this situation, what could we say about this estimate of the green shaded area? We could say it's an underestimate. We could kind of think of this as the idea is that I'm coming up with an upper bound and a lower bound for what the area actually is. The right endpoint was too much, the left endpoint was too little, so therefore I could basically have an idea that it's in between these two values. Is there a point that you think that we might be able to choose that might give me an even better estimate of the area? Instead of picking the extremes, picking a point on the left side versus picking a point on the right side. And, hopefully somebody out there, as you are watching the video, is going to shout out and say, well, why don't we use the middle of the interval? So let's calculate and get our height by using, I guess I should put arrows here, not really equal, by using the midpoint on the subinterval. And if I were to do that, wouldn't you agree that using this rectangle might be quite a better estimate of what our actual area is? That when we look at using the midpoint, I mean, just even visually in this, now I wouldn't say 100% of the time it's always going to be better, but unless it's some extreme weird case, I would say that probably is going to be pretty good. You can kind of see that you can take this little section and flip it and then fill it in over there, and that little section would fill in there. And so that's going to be a pretty good estimate. And then the other thing is that, we're looking at a very simple function here that is only increasing on this. So, obviously in this example, this is clearly the best choice. But you know that you actually don't really necessarily need to pick the right endpoint, the left endpoint, or the midpoint. Those are just special points. I could actually pick any endpoint, so I'll just put a little star, could pick any point, and I'm going to call it C sub I, in the subinterval, that would give me a good estimate. That would give a good estimate of the area. That maybe the midpoint, maybe I decide that it might be better to be a little bit more this way, depending on how it increases or what the shape of the curve is or what's going on. So you actually could pick really any point in there, anything that you think kind of splits it out, and then use the rectangles to calculate it. Now let's kind of come through here and let's kind of talk about these. So what we're going to do is we really are separating this out, and we're using these to calculate the area. So how do we calculate area? We need the width of the rectangle and we need the height of the rectangle. So let's start developing some formulas we're going to use. Now you have an interval, and usually we call the interval a to b. So usually you have f of x on some interval a to b. You're going to set the number of rectangles as n. So let's come up with some general formulas that we're going to use based on that. So if I want to calculate delta x, which is going to be my width of each rectangle here, so this would be, and it's the same in all of these. That may not always be true, but for what we're doing in this purpose, this introductory example, we have the same width. How would we actually calculate that? Knowing I have 4 rectangles and I know I started at A and I started at B. Hopefully you can see that my formula for delta x, I always subtract my endpoints of my interval and then divide by n, and that would give me my delta x. So that's a formula you're going to need to know for your delta x. And then if you think about the height of your rectangle, the height is nothing more than a point that lies on the function. And so you're basically finding the height by finding a function value at a certain x value. And like I said, and I was using x sub I star, I'm actually going to start using f of ci because I think that makes more sense to you. You're going to choose an x equal to c sub I in your subinterval. And technically your subinterval would be x sub, usually x sub I minus 1 to x sub I. 0 to 1, if you consider this to be x0, that would be x1, this would be x2, that would be x3, that would be x4. So you're going to choose some point in the interval to which you're going to get your height from. And your choices that we had is we chose the left for 1, I chose the midpoint for 1, I chose a right endpoint for 1. So your first c sub 1 that you would choose, maybe if I chose the midpoint, would be 0.25. My second c sub I would choose, if I'm using midpoint, would be 0.75, and so on. So you would choose a point in each interval of which you're going to do the height. It could be the same, either the left, the right, the midpoint, or some random one that you're picking. And then you get your height by plugging it into the function. All right? Now, maybe we ought to think about these choices for your choice of this value. Your choices for x equal to c sub I. That if I'm going to choose the left, I kind of need a formula for how I'm calculating it. So I'm going to start with the right, because that was the first one I did up there. So for the right endpoint, now let's think about it in terms of this problem and then maybe work our way up. Okay. So I have my beginning x sub 0, which is really your A. But I want to choose the first endpoint over here. That's the right endpoint. So x sub 1 is what I want to choose first. How do I get x sub 1? Well, x sub 1 we'll do c sub 1 is going to be your A plus you went over one width, right? If I want to get the second one, I need to go over another width from C1. So I end up going over 2 widths from A. To get the third one, you would go A plus 3 of these widths, all the way up to, you get to C sub n, here. Now let's say we're creating a sequence. Think about this as your summations that we were practicing on the other day. We want to get this C sub I in a formula where it's something that I'm going to be able to put in, because I'm going to sum some things up here, right? I'm going to sum up these areas. So I want C sub I, what is my variable as I go through this? You have A delta x, technically there's a 1 there. then you have a 2, then you have a 3, and you're counting up to n. So my variable, my index is I, and my c sub I would be a plus I delta x. So that would be the formula that you are going to use for your right endpoint. Now we look at it for the left endpoint. Now for the left endpoint, your first one is actually going to be a, your second one is going to be a plus delta x, and so on. So you're not quite, you're sort of picking the same values, but you're starting on the left side. So when I get down here to the end, when I pick the last left endpoint, I'm not going to be all the way at the end of the interval. I'm going to be one before that. So it's going to be a plus n minus 1 delta x. So for my formula for the left endpoint, again, putting it in terms of the index, that I'm going a plus 0 delta x, a plus 1 delta x, a plus 2 delta x. Because all of our closed formulas, we have to start I equal to 1. I don't want to change it. I don't want to change I equal to 0. I want I equal to 1 to be my starting point. When I is 1, I need a 0. Oh, so I must be doing a plus I minus 1 delta x. So that would be a formula for my left endpoint. Okay. Now we're going to look at our midpoint, because that one was the best estimate that we had. That if I'm going to choose the midpoint, well, think about how you're getting the midpoint. Isn't it to get the first choice? Aren't you taking the right endpoint plus the left endpoint and then dividing by 2? Okay. And so I'm just going to go down here to the end. I'm taking the left endpoint, a plus n delta x. I'm adding that to the left endpoint, n minus 1 delta x, and I am dividing by 2. This is way complicated, so let's simplify it. So we end up with 2a, and then you have 2 of the n delta x's plus delta x all over 2, and I'm going to simplify a little bit farther, a plus delta x plus delta x over 2. And then you think, oh, wait a minute. Doesn't that sort of make sense that this is your right endpoint? Oh, and this should be a minus, a little negative mistake. The right endpoint minus half the width. Doesn't that make sense to us? So let's use that for our formula. You could have also done the left endpoint plus half the width, but if I was comparing these two formulas, the right formula is a lot easier. And I am missing, that's an I, so this would need delta x I. Delta x I. There you go. So our c sub I is going to be a plus delta x I minus delta x over 2. So if I was doing the midpoint, then that could be a formula that I'm going to use. Now, of course, let's think about this. If you can choose whatever point you want in the interval, if you could choose whatever point and you want to choose the easiest, this would be the easiest formula to use. Easiest formula. It may not be the best estimate, but it will be the easiest formula to use. So we'll kind of put a couple of stars around that one, because given my choice, I am going to want to choose that if I ever have to choose one. However, I do have to show you them all because this is similar to what we did in Chapter 3. While on the AP, you are not going to have to calculate the derivative using the limit definition or any of the alternate forms of the limit definition. There will be multiple choice questions where you have to recognize that if they give you a limit, that it was a derivative because you're recognizing it from your limit definition, whether it's the symmetric form or the alternate form or the original limit definition of a derivative. So the same thing is going to happen here. It's going to be a recognition that if I am going to give you something that is a limit definition of actually what an integral is, that this limit definition that we're going to come up with, we're going to practice doing it the long way, but then we'll never really have to do it the long way on the AP. What we'll see is we'll have to recognize what we have. And sometimes they may give you one that has a left endpoint in it, so I'm giving you the formula so that you can recognize it. All right, now let's talk about this over and underestimate. All right, so right now when I was taking a look at this, what we saw is this idea that our estimate of the area, and actually let's come back a second. Let me finish one more thing here on this page before we move on to the over and underestimate. What was the point of getting these formulas for each of these, kind of building this up? We're trying to find the area, okay? The area under, or let's say between, f of x and the x-axis on an interval a to b. And that what we were doing is that we were basically summing up a number of rectangles, 4 in this case, so 1, 2, however many rectangles that we had, and we're summing up the area of each rectangle. Well, what's the area of each rectangle? How do I figure out the area of each rectangle? I take my width times my height, f of ci. So delta x times f of ci. And let's put an approximation in here, because obviously choosing n equal to 4 is not a great approximation of it, but it's an approximation of it. And then based on our formulas, we could kind of keep expanding this out. We're doing 1 to n of our b minus a over n. We would put in a calculation of what that is. And then our f of ci, whatever our function is, we would choose a ci. For example, I could choose to do the right endpoint. And if I choose to do the right endpoint, I would plug this formula in. A plus I delta x. And again, delta x is our b minus a over n. Now, specifically for this problem, we had f of x equal to our x squared plus 1. We had our n equal to 4, and then our interval was 0 to 2. So what we could turn this into, this area can be approximated by summing the number of rectangles 1 to 4. My delta x, calculate it, delta x is going to be 2 minus 0 over 4, which is going to be 1/2. So my width is 1/2. And then I'm going to calculate f of 0 plus 1/2 I. And if I use the formula rule, I would have 1/2 times my 1/2 I squared plus 1. And then you'll start to see, oh, wait a minute. This is kind of like those formulas that we were playing around with in the review section on summation. That this idea of using sums to calculate the area or to estimate the area, we're going to be looking at things that have our sigma notation, and we're going to be working with them. All right, let's go to this over and underestimate. All right, so right now when we're looking at this, this is our right sum. And with notation we use this, we call this R4, which is going to be an estimate of the area using 4 rectangles and right endpoints. Is that, in this case, going to be an over or underestimate? In this case, it's going to be an overestimate. This R4 overestimates the area. Okay. In this case, and then we need to come back in and start thinking about what that case is. We're going to do, this is L4, taking a look at that, and L4 is the estimate of the area using 4 rectangles and left endpoints. Okay, and this one is going to underestimate the area. And then, of course, this is my midpoint. We would call this M4. So this is your estimate of the area using 4 rectangles and your midpoints. And this one, all we're going to do is say this is better than L4 or 4. We can't really tell if it's over or under. That gets a little gray area there. Now let me have you think about, when is this? How do we know that this is an overestimate? And I can guarantee that at this point in your head, probably 70% of you are saying, hey, the function was concave up. Because that's how we did it when we did estimations or approximations using the linearization, where we used the tangent line. Concave up, tangent line was below, the tangent line was an underestimate of the area, and so concave up comes to mind. But let's think about this. Let me draw another example here. So same kind of idea, except now this time I'm going to make the curve concave down. And I'm going to divide it into the same sections, make my 4 rectangles, and I'm going to draw 4 right endpoint rectangles. So I'm going to come up on the right side and draw that. Come up over here and come across. And now let me ask the question, is this R4 in this case still an overestimate of the actual area that we're looking at? And the answer is yes. So it is not determined by concavity. And then hopefully at this point you're saying it's determined by the fact that the function is increasing. So your right estimate, your right sum, is going to overestimate the area when f of x is increasing, which would be when the derivative is greater than 0. So then likewise, L4, again, would underestimate the area when f of x is increasing or f prime of x is greater than 0. And we don't ever really ask you about when the midpoint over or underestimates. We just know that's a better estimate than what we had. So looking over on the next page then, we want to be very careful not to draw conclusions about choosing the points to affect our estimation. If we know that we are working with a strictly monotonically increasing function, that the right overestimates and the left underestimates. If we are working with a strictly decreasing function, then we know that the right will underestimate and the left will overestimate. But now the idea of that every function only does one thing on the interval is usually not likely to happen unless they've manufactured it. And in that case, if the function both increases and decreases, we would not be able to determine over or underestimate. On the AP, they would only ask you for an over or underestimate if this were true. It was only increasing or only decreasing. All right, but now, of course, looking at these estimations that we're coming up with, how close is this to the actual area? It's not great. It's just an estimate of the area. These left sums, right sums, and midpoint sums that we're coming up with are not a great estimate. We want a better estimate. Just like when we were calculating instantaneous rate of change, using the average rate was a good estimate, but the average rate is not a great estimate for the instantaneous rate. What did we do? To get better and better approximations, what we're going to do is we're going to make more rectangles. We're going to increase n. We're going to let n go to infinity. Here is our limiting process that we were doing in calculus. That's the calculus part of this. We're going to let n go to infinity. And so we're going to calculate this. Now what I'm going to do, just in this example, here's 8. And we're calculating this area under the same curve. Now I could have done the calculations using the 4 rectangles. We could have actually done each calculation. Let's just show you how you would do this on the AP. If they ask you to calculate, let's do the right sum, which is an overestimate. That if I was going to ask you to calculate the area, so they would say estimate the area under the curve f of x equal to x squared plus 1 from 0 to 2 using right endpoints. Here's what you would show as far as your work. You would say R8, or actually technically we would start by labeling what we're finding. So I would say that the area between f of x equals to x squared plus 1 and the x-axis on the interval 0 to 2 is approximately found by doing R8. R8 is going to be the sum, I equals 1 to 8. We're doing 8 rectangles. I need my delta x. Maybe I'll come up here. Delta x would be 2 minus 0 over 8, or 1/4. So I can write it as 1/4. Times my f of my c sub I, using my right endpoint, would be 0 plus my delta x times I. So I'm doing f of 1/4 I. So that's writing it in summation notation. I equals 1 to 8 of 1/4. And let's go ahead and put the function in. Our function was x squared plus 1. So we would have 1/4 I squared plus 1. All right. But now we're doing 8 rectangles. So I'm just going to come down here a little bit. Let's actually write it out in expanded form. Now typically what the AP does is they never ask you to do a left sum, a right sum, or a trap sum with more than maybe 3 to 5 rectangles. We're doing 8 just because that's where I'm at in the notes, but usually on the actual AP, 3 to 5 would be plenty, and usually you are going to write it out in expanded form. So you basically go, hey, I know, I can identify once, you can do it by formula or you can do it by common sense once you label it out, since it was only going 0 to 2. I can tell my right endpoints. There's my first one, my second, my third, and so on. So I have all of my right endpoints. I know that I'm going to do 8 rectangles, and I know the width is 1/4. So this R8, if I expand it out into expanded form, is going to be, I like to only write delta x once when I'm doing this. So I usually go delta x times, and now I'm going to do the heights. And so in the calculus, we don't care about actually simplifying. I could put it actually in the formula, but usually you just go, oh, it's going to be f of 0.25 plus f of 0.5 plus, and you continue plugging in each of your right endpoints, f of 1, f of 1.25, f of 1.5, f of 1.75, and f of 1. And you do make sure that you have 1, 2, 3, 4, 5, 6, 7, 8 heights for your 8 rectangles. And you've got your delta x that you're going to distribute through. And then at this point, you would simply go, hey, calculate it, and get your 5.1875. You can verify that. What they want to see on the AP when you do a problem is that you've labeled it, you're showing that you're doing the right sum, and they actually don't even care about the sigma notation. They just care that you can write it out in expanded form. They do not need to see the actual y values here. Knowing that you are plugging the right endpoint into the function is enough for them, and then you would calculate this using your calculator. Okay. Now, taking a look at that, and you can verify on your own that you do get your 5.1875. I want better estimates, okay? And so to get better estimates of this, what I am going to do is I am going to find, maybe I want to find the area exactly. So to find the area exactly, what I'm going to do is not set it to be 8 rectangles. I'm going to leave it as n rectangles and take a limit as n goes to infinity. Now we will do that at the end of this set of notes. What I want to do now is just practice the approximating using a right sum, a left sum, and so on. All right, so what I'd like you to do, here's example 2. And this is basically just kind of very similar to what we did. Right now, what I want you to do is I want you to stop the video, and I would like you to estimate each of these items. Don't worry about T4 yet. I'll talk about that myself. But what you're going to do is you're going to basically come in, and for your L4, and you might need more room, or you might need, we'll write it up here. Take your L4 and put your formula for L4 given this information. We want 0 to 1. 0 to 1 is our interval, and our function is x squared, and we want 4 subintervals of equal width. I'm going to underline this because later on we may not have equal width, but right now we're using 4 subintervals, 4 rectangles. So we want a formula on how to find the left endpoints. In other words, what is your, maybe I should say C sub I. What's a formula for C sub I if you are going to do the left? Give me a formula for C sub I when you're doing the right for this problem. Give me a formula for C sub I when you are doing your midpoints here. Then I want you to actually list them. There's only 4 of them, so do C1, C2, C3, C4, and list them for the left, for the right, and for your midpoints. Then what I want to do is you basically, somewhere at some point in order to do this, hopefully you realize you've calculated your delta x. So make sure you tell me what your delta x is. And I don't want you to write the limit notation here because I don't want you to write the summation notation. I want you to actually do each one as your expanded form. So I want you to go area is approximately, we're going to do L4, and you're going to give me your delta x times, so you'll fill that in, and you have 4 values right here. And just go ahead and put it in F of notation so we see it. Then calculate it using your calculator and give an answer. Then do your right sum. Same thing, delta x times, fill that in, give an answer. Calculate your M4, fill in your delta x, fill in your notation for your expanded form, and then give an answer. And then we'll come back and I will talk about the T4. So pause the video. Alright, so you can check your answers with mine. Here's my formula for my left and my 4 left endpoints, my right, 4 right endpoints, and then my midpoints. I prefer fractions because I feel like writing the decimals out, and it was easier for me to understand this as fractions, although decimals are certainly fine. So the area can be approximated with the left sum, and then this would be what we would write down for the AP. And then you get the answer however you got the answer using your calculator. Now you could have individually plugged 0 in, plugged in 1/4, plugged in 1/2, plugged in 3/4, added it up and done it. I kind of, when I did it, basically used the summation on my calculator. I just wrote it as 1 to 4 delta x f of my left endpoint formula and plugged that into my calculator. And then I did the same thing for these as well. So you can plug and chug, or you can use the summation formulas on your calculator. Now the T4, okay, and this is an introduction more actually from section 5.6. These methods that we're doing, where we're approximating the area, these are called numerical approximations. And there are a lot more kind of topics in that section 5.6 than what I'm going to show you, but for the AP, okay, let's talk about a difference between your textbook and the AP. The AP only requires that you be able to do a left sum, a right sum, a midpoint sum, and what's called a trapezoid sum. This is called the trapezoid rule. And so we're going to look at the trapezoid rule, or trap sum is what we're going to call this one for short. And the trap sum basically is, we're going to change our perspective a little bit. Instead of using rectangles and calculating the area, what we are going to do is we are going to estimate this area by using trapezoids. And remember with trapezoids, I'm going to kind of draw in a representative one right here in the middle. That trapezoids have 2 parallel bases, and then two parallel sides, and then 2 sides that are not parallel. So notice what I'm doing here is I'm connecting the left and the right. And so I end up with what would be a great approximation, right? If we go through and we draw a trapezoid in, and this last one, yes, it's a triangle, which is nothing more than a trapezoid with a zero height when you're looking at it, or a trapezoid where one side is zero, that you get a much better approximation of the actual area by doing these little trapezoids. Now, from geometry, and what I've learned in all my classes is y'all don't know your formulas for area of a trapezoid. So area of a trapezoid is going to be 1/2, or actually, let's write it as we take the first parallel side plus the second parallel side. Usually we call those the bases. You average your bases, and then you multiply by the height. That would be if I'm thinking of the trapezoid as I have two bases that are parallel. This would be B1, B2, and then of course the height would be that right there. So you average your two bases and then multiply by the height. And so what we will see here is that this trapezoid is, turn it on its side. This is actually a base, this is a base, and then this right here is your height. So your height is actually your delta x. Your B1 is going to be your f of your left endpoint. So in this case, this would be L3. And then this one would be the height for the right endpoint, so that would be f of R3 that you're using for your right endpoint. And so the idea here is you could come up with a formula, and then you would add up all your trapezoid areas instead of adding up your rectangle areas. Well, we don't want to have to calculate the area of each trapezoid individually. We've already done a lot of work. What I want you to realize is, what if I were to draw in, here is the right rectangle, okay? Here's my left rectangle. So I have a right rectangle that's too big and a left rectangle that's too small, and the trapezoid kind of cuts right in between the two of those. And hopefully that you can see that if I'm basically doing this sum of the area of the trapezoid, let's put this in terms of our notation that we're using. So we would take our f of the left one, L3 point. I know that's bad notation there, but you kind of go with what I'm going. You know, I guess I should do CL3 or whatever, but you know, the left one, plus f of the right one. We're going to divide by 2, and then we're going to multiply that by delta x. But that's exactly the same if I distribute as delta x times f of the left endpoint plus delta x times f of the right endpoint, all divided by 2. And if I were summing these up all the way across, isn't this nothing more than the left sum plus the right sum, all divided by 2? All I'm doing is averaging the left and the right sums. So when we do the trap, and that's why there's adding them up individually, but we never do that. We always just calculate T4 by doing left plus right divided by 2. So at any point, if they come in and they say calculate T4, all you need to show, like in this example, would be that T4 is going to be 0.21875 plus 0.46875 and divide by 2. And then we're done. And you calculate it on a calculator. So that's how we're going to do the trap sum each time that you are asked to do the trap sum. All right, so now kind of what we want to do is say we want better approximations. So we're going to do more intervals, and we're going to let n go to infinity. And so what we're going to end up with this, and you can kind of see in my illustrations here, better and better approximations. And it actually does not matter that if we are going to let n approach infinity, the choice of an endpoint, the choice of c sub I is completely arbitrary. That it's not going to have any effect whatsoever on the fact that the approximations that we're doing are going to get better and better and better. and that when I take this limit, it's going to converge on the true value of the area. And so that is this idea of what we're going to do. Now, example 3, I'm going to leave that for you to do on your own, that you would estimate this area, use 5 subintervals, and do the 3 cases. And by 3 cases, I want you to do a left, a right, and a midpoint. And then at the end, go ahead and add in T5, so we'll do 4, just so that we can practice doing that one. So this one I'm going to leave for you to do on your own. What I want to do now, since I'm talking about finding the actual area, go to the general case. How do I find exact area using limits? So what we're basically going to do, and what we'll practice, is that, again, we're starting out with the function being positive on the intervals so that it's above and we're calculating a positive area. We calculate our delta x, dividing it into subintervals of each length. We are going to look at our endpoints of each of the intervals, and then we basically, from each of these little subintervals that we have, we're going to choose a point, and remember I was changing these to be choosing C sub i's in the interval. You can choose a left, you can choose a right, you can choose a midpoint, or any point in between. Okay? And they don't actually have to occur at the same point, but for ease of convenience in our calculations, we may decide that when we do it, I'm going to choose these C sub i's to be the right endpoints. And that if I were to take the height times the width of each rectangle and add them up, I would get an approximation of the area. But I don't really want to approximate this area, and here I've taken it from expanded form to sigma notation. And again, I'm using, if it helps you when you're looking at these, that this is f of C sub I, delta x, that after I put this in its sigma notation, this summation that we have is called a Riemann sum. A Riemann sum named after a mathematician, German mathematician Riemann, that this Riemann sum approximates this area. And if I want a better approximation, I want to let the number of rectangles increase. So I'm going to take the limit as n goes to infinity of this formula, and then it turns into the exact area. Okay. Now, I'm going to skip what's below for a second. What I want to look at is pause for just a second. Let me find the... All right, so here is this example, the one that we started at the beginning. We were finding we had that x squared plus 1 graph, and we were going from 0 to 2, and then we wanted to calculate this area. So that was the problem we started this set of notes with. So what we're basically trying to do, and ignore the top part right there, just down here at the bottom, I wanted to calculate that area. So the first thing we do is we calculate delta x, so that's here. You can determine the subintervals, but that's really not an important thing. You're going to choose a point. Now, how did I choose this point? You're going to pick x equal to ci. It's always easiest to pick the right. So c sub I for the right would be 0 plus my delta x, which was 2 over n times I, which simplifies down to 2 over ni. So that's this right here. That's me picking the right endpoint, mostly for convenience. Then we're going to write the area as the sum of the rectangles. So we take our height times our width and we add them up. So we're doing f of 2i over n, that's your c sub I, times your width, and then I plug it into my formula, so that gets to here. Now remember those skills that we learned, that we can now expand this out, and now I want to find the exact area by finding the limit. So to do that, what you're going to do is you're first going to get rid of the sigmas, like we did before, combine it all together into one rational function, and then we are going to take the limit as n goes to infinity, and clearly see that dominant over dominant, our answer is 14/3. And you can compare that to the areas that we came up with in the notes. But we'll do several more examples of this next class, but let's stop this video here. Kind of coming back to talking one more thing. Sorry, I was going to stop and then I realized I still need one more thing to talk about. That we do have to talk about the idea that these Riemann sums do not always give us area, however. That the function that I was picking at I was requiring it to be positive. But many functions are not always positive. And so, like if I was doing this case, when I do this Riemann sum, it's not going to give me positive values, it's going to give me negative values because these are negative numbers for these function values that you have here. So area is always positive. A Riemann sum is going to be negative in some cases. And so if I wanted area, you would have to convert into a positive number so that you would have area. So that's something that we're going to discuss more in the next set of notes. Now the other thing that I kind of want to talk about here is why do we keep talking about this area problem? That how is it related to what we actually want to find, which we're in the integration section? How is this related to integrals? Well, we're going to introduce, and this is going to be in the next set of notes, the idea that if I wanted to actually calculate this Riemann sum here, and then take the limit as n goes to infinity, that we're actually going to get a definite interval. And you can actually check on the calculator that we actually have that as a command on our calculator. So take a look under the math menu, and notice that number 9 here is function int. That is an interval that we've been working on. But it is not an indefinite interval. It is what we call a definite interval, that it's going to give us our bounds. And so the number that we just found, we were doing the 0 to 2 were our a to b, our interval. The function that I was dealing with was x squared plus 1. And our delta x is our change in x. And that this summation, this limit, is actually an integral, but we call it a definite integral because we're not doing an antiderivative here. We're actually finding an area, and that if I were to hit the enter, I would get the same answer that I got, type in the fraction that we came up with earlier, the same answer that I would have gotten there. And so integrals in this area are directly related to each other. Yes, this will have something to do with those antiderivatives we were doing in 5.1, which will come in a later section. So now I'll stop and we'll pick up and talk more about this definite interval next.